So I think it's 3 o'clock and I think we can proceed. And so I guess Isaac is going to go first and then Danielle.
Okay.
And go ahead, share your screen.
Okay, we'll do. Can everyone see my screen okay?
It's fine, it's fine.
Yes.
Okay, awesome. I'm Isaac Lawanson, and in Professor Alejandro's group, I'm a second-year master's student in power systems. And this presentation will be about my project on offshore wind turbine converter reliability. So the structure of the presentation will be talking a little bit about the reliability model of the existing architecture, the baseline architecture, and then I'll talk about the things that we have designed as a group and their reliability and their availability, and then I'll move on to sensitivity analysis, where we'll discover which components of the converter have the most impact on the failure rates and the reliability of the system. So first off, we have these three architectures that we're going to be looking at for the rest of this presentation. We have the baseline architecture, which is what we're using to run our comparison with. Has 6 active switches and 1 capacitor. And then we have the proposed architecture, which has 3 passive rectifiers over here, 1, 2, and 3, and then this active rectifier. In total has 24 diodes and 12 active switches and 2 capacitors. And then we have this proposed architecture with bypass structure that is pretty much the same as the proposed architecture, except this bypass switches over here. They are for isolating failed passive rectifiers so that the system can still produce power when one of these passive rectifiers fails. So all of these converters have a failure condition if their capacitors fail, or if for the baseline, if one of the 6 active switches fail, or for the proposed architecture, if one of these diodes fail, or these diodes or these active switches. But for the proposed architecture with bypass, what's interesting is that if any of the components in this active rectifier region fails, then the system has failed. But if one of these fail, if one of these diodes in one of these 3 passive rectifiers fail, the system can still operate because of these bypass switches. And the advantage of having these passive rectifiers, is that we're reducing the voltage that is seen by the active rectifier, and therefore reducing the failure rate of the components in the active rectifier. So for all the converter architectures, I said that they all have capacitors. So there's some failure states that are associated with the failure of those capacitors. And we quantized the capacitor's life into these 4 stages. This first stage is the longest stage of its life, where the capacitor drops from one normalized capacitance to about 0.97, and then the next stage from 0.97 to 935, and it's a little bit shorter in length, and then from 935 to 0.895, before the last stage where it's like where we consider it to be failed when the normalized capacitance is less than 90%. And this affects all the different architectures that I showed earlier. This next slide shows a representation of a Markov model showing the possible states of the system and the conditions for the transitions of those states. So we have state 1, which is when the converter is working exactly the way it's supposed to be. And then we have stage 2, which is if any of the switches or if any of the diodes fail, then the model goes to stage 2. But if it actually just degrades if the capacitor just degrades to that first level, then we go to stage 3, and then from 3 to 4 if one of those components fail, and so on and so forth. And the below it is the Chapman-Kolmogorov equations, and the solutions of these equations leads us to the occupational probabilities of each state at the end of a certain amount of time. So when we solve these equations, we can get an idea of what position the system will be in after a certain number of time. All the calculations that are done in this presentation are for time equals 30 years, but you can vary the time to see what happens for even longer. And the only major difference between the Markov reliability model for the baseline and the proposed architecture is that the proposed architecture has more diodes and more switches and an additional capacitor. I would also like to point out that lambda AR doesn't just contain the diodes and switches, but also contains auxiliary systems that are in the system, like the control modules and so on and so forth, the protection systems, things like that. And then this next slide is showing us the Markov model for the proposed architecture with bypass. Because it doesn't fail, we've seen from left to right the failure of the capacitor going stage 1 to stage 2, stage 3, but then going up, we have these transition states that show what happens if one of the passive rectifier fails. So when one passive rectifier fails, we have this transition to this blue region where we're only producing 75% of the power. And then if another passive rectifier fails, so now we only have one passive rectifier and one active rectifier, then we have this yellow region. And then if all the passive rectifiers have failed, then we have this brown region where only active rectifier works. But note that for all these stages, if at any point the active rectifier fails, then we will just go into a failed state. So that's why all of these points, or that's why all of these balls from 1 to 12 have a state that connects automatically to a failed state of the active rectifier. The repair strategies that we looked at to calculate our availability for the baseline and proposed architectures are as follows. We're focusing on the capacitor and the capacitor's life. So for all of the active rectifier positions, if it fails, then we fix it at a repair rate of mu AR. But for the repair strategy 1, we fix the rectifier if the capacitor has completely failed. For repair strategy 2, we fix it if it has completely failed or if it has reached 0.35 of its nominal value. And for repair strategy 3, we fix it if it has reached 0.97, 0.935, 0.97 of its nominal value, 0.935, or if it has failed. And then for repair strategies for the bypass, we're looking at 2 strategies. The first one is one that only works if we can repair the converters while the wind turbine is still in operation, which is we'll just repair the passive rectifiers one at a time. And then we also have repair strategy 2, which is when we would have to turn off the wind turbine, and we would just repair all the passive rectifiers that have failed in that period in one go. So those are the 2 repair strategies that we're looking at for the proposed architecture with bypass structure. So these are the results that we got from those initial calculations. We see that the baseline performs just a lot worse than the proposed architecture with bypass. We see, it's almost 10 times more than the proposed, and the proposed bypass is even 10 times less than the proposed. So we know that over 10 years, we're expecting the failure rate of the converter to be about 0.0021 fails per year. And then right below that is the system level failure rate. So if we're including all those auxiliary systems that I was talking about, such as the cooling system, protection system, and control modules, then the numbers go up a little bit more. They're more significant for the baseline than for the proposed and proposed bypass structure because of those reductions in voltage, and those reductions in voltage cause a very big reduction in the failure rate of the components. And then the graph below just is a graphical representation of what we've seen up top. And we see this interesting thing that happens at the beginning of the baseline, but it doesn't occur for the proposed and proposed with bypass because the failure rates are so low that we don't even actually get to see that trend over the first 30 years. And this trend is as a result of the capacitor failing, the first stage of the capacitor having a high rate of failure in those first 10 years. But because of the reduced failure rate for the proposed and proposed bypass, we don't see that trend in the first 30 years. And then these show for the different repair strategies how available we expect the converter architectures to be. So for repair strategy 1, for the baseline, we expect it to be 0.9981% available. And then for repair strategy 2 and 3, 0.9991. But for the proposed, there's actually very little change between all the different repair strategies, showing that even the least aggressive repair strategy is still better than the highest aggressive repair strategy for the baseline. And then for the proposed with bypass, both of them are pretty much comparable and are much better than the proposed and the baseline architecture. So here, these are some graphs that just show the numbers that I presented on the screen earlier. Obviously, if there's no repairs, then we expect the availability of the baseline to go to 0 at time equals 30 years. But there's a slower curve for the proposed architecture. And then right below these top graphs for baseline and proposed is just the zoomed in versions of this red graph up top, where we remove the no repair strategy. And here we see that 0.9981, and here 0.9991, and then for these guys the 0.9995. And this hitch right here is just because of resolution. It's actually a very smooth graph. If we zoomed in, we would see that's actually very smooth. So we can see that repair strategy 2 and 3 have like very minimal impact on the system. And for proposed architecture, we see that there's almost no impact at all. And then for the proposed with bypass, as we said before, repair strategies 1 and 2 pretty much are the same, and it has the same effect in both availability on this left-hand side and on the right side, the power produced. So whether it's that 100% power produced, 75% power produced from those blue parts of the graphs, those blue parts of the representation, or the yellow parts 50%, or the brown parts the 25%. They have repair strategy 1 and 2 both act the same, and they're both much higher than the proposed architecture and the baseline architecture. And then onto the milestone that I worked on as well was sensitivity analysis, and this will tell us which components have the most impact on the failure rate and the availability of all those converter architectures. So this is looking at the system level failure rate and what impacts it all the most. On the left, top left, we have the system level failure rate of the baseline. On the right, we have the system level failure rate of the proposed architecture. And at the bottom, the failure rate of the proposed architecture with bypass. And we can see that there's a trend. This red line here and this purple and red, and this purple and red are from diodes, and the failure rates of diodes and the failure rates of active switches. So if we multiply those failure rates by up to 10, while holding all the other failure rates constant, we expect the system level failure rate of the system to increase by this much. But what's super interesting is that for the baseline, it goes from 0.8 to 1.2, about 1.9 for the increase of the active switches by up to 10. But for the proposed, it's less than 0.1 to 0.35. And then for the sensitivity of the proposed with bypass, we see from less than 0.056 to 0.066. So even when we increase the failure rate of, the active switches or the diodes by up to 10 times, the impact on this overall system level failure rate is still is very negligible compared to, for example, the baseline where it almost doubles, or actually more than doubles. And then now we'll focus particularly on the baseline for just a little bit. We're comparing repair strategies. So on the left is repair strategy 1, and on the right is repair strategy 3. And obviously the one that's more aggressive causes, we expect less impact on the system level failure rate. So this number here is 0.99725 when we increase that active switch by up to 10 times. But here it's 0.99625. But all the capacitors pretty much, because we're repairing the capacitors more often with this repair strategy, we pretty much see no capacitor, we see very little impact on the system level failure rate when we increase the failure rates of the capacitor. On the bottom, we have the graph showing us changing the repair strategy or changing the repair rate, like reducing it by up to 10 to the negative 3 times. And we can see that obviously if you are not repairing the system, one or the other, whether it's the active rectifier sides with all the diodes and switches, or if it's the capacitor, then we expect very low availability, 0.5. And then for repair strategy 3, same thing. But because there's more repairs on the capacitors, then we see that this is a little bit smoother, longer before it drops off. For the proposed architecture, we only put repair strategy 3 because repair strategy 3, it looks exactly the same as repair strategy 1 and 2. And we see what we expect where the diode is has the most impact on the availability if it's increased by up to 10. And for the repair rates, we see that now the capacitor, even if we reduce the repair rate of the capacitor all the way to 10 times negative 3 of that repair rate, it's still hovering around 1 because the capacitors are pretty much not failing compared to the active rectifier. If we reduce that, it drops to 0.65. But compare that to the baseline that was dropping all the way to 0.5. And then for our proposed architecture with bypass, we expect like much higher numbers for them. And even when we increase the diodes and the active switches by up to 10 times their failure rate, the drop is still above 0.998 for repair strategy 1 and 2. Repair strategy 1 and 2 have pretty much the same graphs. And then for at the bottom where we have impacting the repair rates, we see the same trend where the capacitors are having 0 effect pretty much, and also the passive rectifiers on this one as well. Even when we reduce the passive rectifier repair rates by a lot, the availability is still very high. For the repair rates of the active rectifiers though, if we reduce them by up to 10 to the negative 3, they only drop to 0.86 compared to the 0.65 of the proposed and the 0.5 of the baseline architecture. So our main takeaways from the sensitivity analysis was component importance, obviously noticing that the active switches and the diodes play a very important role in the design of the converters. And if we can get things of the best quality, then we will have a more reliable and more available converter. And design justification, just proving that our architecture that we designed is better than what is the existing alternative. And choosing one in particular, obviously the proposed architecture with bypass structures, because it outperforms both the baseline and the proposed architecture. So that is the end of my presentation. And feel free to ask any questions. I know Daniel is going to be presenting after me, so I don't know if he's supposed to present first before people ask questions, but the floor is now open.
Can you hear me, by the way?
Yes, Daniel, I can hear you.
Okay. Should I start then? Yeah, okay.
Go ahead, Daniel, start.
Okay, can you see it? Yeah, right. Okay, so my name is Daniel. Just to give you a little bit of context, like we all together are working on the design and the study of a new proposed direct drive PMSG. Basically, my part, what me and my advisor, Professor Gross, are doing is make an economic assessment of this new proposed design. And mainly, most of the time, what we are doing is comparing our results with the results of the reference design. So here are the milestones of this quarter. We have milestone 5.2 and milestone 5.3. One is more related to the data collection of the proposed design, and the other is more related to the performance cost analysis. It's a lot to read, so here I put a slide where I made a summary of the main tasks for this quarter. First, we have to calculate the design cost density of the proposed system and compare it with the value that appeared in the proposal, which is $164 per kilowatt. Then we calculate the operational maintenance cost of the reference and the proposed design, and we compare them. And the third task will be compute the performance metrics, which in this case will be expected annual energy generation, capacity factor, and LCOE, also for the reference and the proposed design under different simulated wind regimes. And finally, we will also compare the annual energy yield per total cost of the system with the value that appears in the proposal, which is 22.24 kilowatts hour per dollars. Here, before going through the outline and all the information that I'm going to provide, I wanted to make sure that we understand that we made a revised preliminary estimate, since the power electronic cost density of, okay, I think this you can see, no, sorry. Okay, I wanted the pointer, sorry. So the power electronic cost density of $40 per kilowatt, it's an inaccurate objective for us in terms of power electronic cost density. So we have decided to use a different power electronic cost density as an objective, a more realistic objective. And this is actually a number that appears in the literature, in the state of art, which is the NREL paper. And with this change, we could say that the new design cost density of the system that we propose as preliminary estimate is $338 per kilowatt. If you change the preliminary estimate of the cost density, you will also change the energy yield per total cost of the system. So what happens is that for the preliminary values, we will obtain that the annual energy generation, the expected annual energy generation was 36 gigawatts hour. But if we use the new cost density, divide the expected energy generation by the new cost of the system, the energy yield per total cost of the system now becomes 10.79 kilowatts hour per dollars. And this is something that we will see through the presentation. We have changed these new numbers, and we have said that this is the revised tasks that we have for this quarter. Now we can move on with the outline, and we will see that in the beginning we will present the key metrics that we are going to be addressing. And then we will present the challenges that we have in terms of the data that we have to provide in terms of the power electronic cost, PMSG costs, total fixed cost, which will be calculated by using Orbit, which is a software from NREL. Then the operational maintenance cost, incorporating the reliability data that ISAC is providing. and finally the performance metrics. And one final point, which is not part of the milestones, but as the Branjan, which is other member of the group, is working on a wind farm without an offshore substation, where we are going to provide an economic analysis of a comparison of a wind farm with offshore substation versus a wind farm without offshore substation. The key metrics that we are going to study are, of course, LCOE, which I would say that is the most important metric to address, like to represent the economics of a project, energy project. It is calculated by multiplying capital recovery factor by the fixed cost of initial investment in dollars per in dollars, plus the annual operation and maintenance cost, all divided by the expected annual energy generation in kilowatts hour. Then the cost density of the system in dollars per kilowatt is calculated by dividing the cost of the system in dollars by the rated power of the wind turbine, which in this case is going to be 10,000 kilowatts. And the annual energy yield per total cost of the system in kilowatts hour per dollars is going to be calculated by dividing annual expected annual energy generation by the cost of the system in dollars. Here in these two slides, I wanted to briefly show you from where do we get the data from. Basically, the capital recovery factor that we use is 0.082, which is the default value that appeared in Atlantis Metric Space Workbook, which is a software that we are using. For the power electronic cost, we calculated the cost of a 200 kilowatt converter and then linearly scaled those costs up to a 10 megawatt converter. For the PMSG cost, what we do is that we took the masses from the PMSG design and multiplied by the unit cost of each of the materials of the generator. And those unit costs that we are using are taken from the NREL paper, which is the state of the art. And the total fixed costs are computed by using Orbit, which is a tool that I will show, and I will try to explain you how it works. For the annual operation and maintenance cost, we use the same methodology that we use in the previous quarters. Basically, we take the reliability data from the proposed design and combine it with data of an offshore wind farm that has 5 megawatt wind turbines, and then scale those costs up linearly to those of a 10 megawatt level. The performance metrics, LCOE, capacity factor, and expected annual energy generation are calculated by using Atlantis Metric Space Workbook. The challenges addressed, we will move on with the power electronic cost first. As I said, we evaluate the component cost of a 200 kilowatt converter, and we scale those costs up to those of a 10 megawatt converter. We include additional expenses to cover for research and development costs, labor costs, and profits. Here, I will say that we made really conservative assumptions, since we use 7% of the cost to cover for research and development costs, while companies use typically 7%. 30% of the power electronic costs are going to cover labor costs, when such costs range from 20 to 35%. And 13% of the power electronic cost will cover manufacturer profits, when the historical maximum share for Vestas was 30.18%. And again, another conservative approach, we haven't taken into account economies of scale when we could have done that. So what we have done is scale the cost of the 200 kilowatt converter linearly to those of a 10 megawatt system. And again, I think that is a really conservative approach. So here are the components that we are using. Of course, we have the cost in dollars per unit and the number of units. And here we obtain the cost in dollars of each of the components. And right here, we have the component costs of the 10 megawatt level and the 200 kilowatt level, and the additional cost with their corresponding percentages. What we obtain is that the total cost in dollars per kilowatt is $48.17 per kilowatt, while the power electronic cost of the NREL/DTU design were $230 per kilowatt. What we see is that we have had a huge decrease in terms of power electronic costs. So I would say that this is good news for our generator. Then moving on to the PMSG costs. Here in this slide, I wanted to show that we use the same unit costs for each of the materials of the generator as, I mean, we use the same costs that appear in the NREL paper for the reference design and the proposed design in order to make a fair comparison. And I wanted to remark that the permanent magnet unit cost is in another order in comparison with the rest, just to point that out. And here we have the information that we have of the reference design and the proposed design in terms of the masses of each of those materials in the generator. And we should remark that the mass of the permanent magnet mass of the proposed design is around 5 times bigger than the mass of the reference design. And that is going to have a huge impact in the cost. And also I wanted to remark that the total mass of each of both generators are mainly similar. And here we see the impact. This is the formula that we use to compute the fixed cost of the PMSG costs. And we observe that the cost of the proposed design is around 4 times the cost of the reference design. Again, I wanted to explain that we shouldn't worry about that because we will see in the following slides that even though the generator is a little bit more expensive than what we expected, we will get to accomplish the milestones, and also thanks to the generator, we will have a lower power electronic cost, a better efficiency for both components, better availability, better reliability. So in the end, we will have lower LCV values for the proposed design. And here in this slide, I wanted to show that if you add up the PMSG cost and the power electronic cost, we have accomplished the milestone. We have a value in dollars per kilowatts that is below the value that was as a revised preliminary estimate. So we can say that the first task is successfully accomplished. Now moving on to the total fixed costs. For the total fixed cost, we use a tool called Orbit, which is a tool that calculates the balance of system costs of every wind farm or every offshore wind farm, and it takes into account the substructure that you are using. This could be any of these types of substructures, the score protection system that you are using. If we use a mooring system, we include the mooring system in the simulation, the offshore substation that we are using and the location of the offshore substation, the array cable system, the types of cables that we use for the array and export cable system. And it takes into account investment costs, of course, and the installation costs, which also include the turbine installation costs. Here I just wanted to show that, of course, there's a huge difference depending on the substructure that you use for your wind turbine. And here you can see the different types of substructures. And here I just wanted to show you that there are different components in the wind farm. The export cables, which are the cables that connect the onshore substation to the offshore substation. The array cables, that are the cables that interconnect the wind turbines and connect the wind turbines to the offshore substation. Of course, the offshore substation, which is the substation that transforms the voltage of the array cables to the voltage of the export cables. And this tool also takes into account the vessels, the types of vessels that we used for the installation of each of these different components. Here, I will go more fast on this one. Here, what we do is we study 2 case scenarios, where basically in both case scenarios we have the same characteristics in terms of the type of wind farm, same types of wind turbines, distance to shore, platform, sea depth. But the only thing that changes is that we use a reference system, a reference 10 megawatt system for one case scenario, and for the other we use a proposed 10 megawatt system. What happens is that the only thing that changes is the investment wind turbine fixed cost, which will be $1,255 per kilowatt for the reference wind turbine, and a bit more expensive due to excessive cost of the generator for the proposed wind turbine. And here again, we will have the same characteristics in terms of array cable systems, sport cable systems, offshore substation, and the barges and vessels that we use for the installation. Here, there's an example of the fixed cost components. What we observe is what I was already saying. The only difference is in the investment wind turbine costs, where we see that the proposed design is going to be a little bit expensive, a little bit more expensive. And this is the case of the fixed cost of a wind farm with 110 megawatt wind turbines. Now we will see the economies of scale. Will represent the fixed cost in dollars per kilowatt, depending on the number of 10 megawatt wind turbines in the wind farm. And we will see that there's a constant difference, the difference that I was talking about before, and that the wind farm with wind turbines incorporated in the proposed design is going to be a little bit more expensive. Once again, I repeat, this is not going to affect negatively, like in a negative way, the LCOE values, since we will have a generator with more efficiency, more availability, better failure rates. So we shouldn't be worried about these results. Now moving on to the operational maintenance costs with incorporated reliability data. Basically, we changed the reliability modeling data of 3 components: the power electronics, the generator, and the gearbox. This is the data of the reference design. And the main things that changes from one design to the other is that we use the reliability data of the proposed design, which you can see that the failure rates are much lower. And we assume that the failure rates of the gearbox are going to be 0, since in our design, we won't have a gearbox. Also, we use different probabilities of occurrence of the types of failures that could happen to the power electronics and the generator, since that thing, I mean, that also changes for our proposed design. Here we obtain the final results, and what we see is that if we compare the proposed wind turbine design to the Atlantis floating offshore wind turbine, our design has an operational maintenance cost that is 35% lower. And we observe also that if we compare the proposed wind turbine design to the reference wind turbine design, there's an 11% decrease, which is a pretty good decrease, taking into account that you are only changing 3 components out of all the components that a wind turbine has. So we could say that we have accomplished the second task. And moving on to the performance metrics. No, sorry. Now there's like a introduction just to make sure that we understand that even though the fixed costs are higher for the proposed design, as you can see, if we compare, this is reference design and this is proposed design, as the operational maintenance cost also change, finally what we obtain is that the number in the numerator for the proposed design is always going to be lower in comparison with the reference design. So this is obviously good news for us. But if we take into account that in the denominator, we're going to have the annual energy generation, these are even better news for us because, as I've been saying, we will have better efficiency and better availability that will provide us a higher annual energy generation. Now, moving on to the performance metrics, this time I will go. We obtain performance results for the reference design and the proposed design, and we determine the wind probabilistic wind regime by using a Weibull probabilistic distribution. And what we do is that we vary the Weibull scale to simulate different wind regimes. Here we have the parameters for each of the designs, the key parameters. These parameters are taken from the work of the PMSG team and the power electronics team, and also from the availability is taken from the work of ISAC. And here, these are the 5 types of simulated wind regimes that we are going to study. A will be the less advantageous, and A++ will be the more advantageous for harvesting energy. And as I was predicting, the expected energy generation of the proposed design under 5 different wind regimes is going to be always better than more than the expected energy generation of the reference design. And as the capacity factor is a function of is proportional to the expected energy generation, also the wind farm with wind turbines incorporated in the proposed design are going to obtain higher capacity factors under 5 different simulated wind regimes. And here in this slide, I wanted to show this is a more complex calculation because it also takes into account cost components. But basically what we observe is that the economies of scale are well represented, and that if we compare the LCOE values of a reference design and a proposed design under the same wind regimes, we will observe that for A wind regime, the reference design obtain higher LCOE values than the proposed design, and it will happen the same for all the wind regimes that we have simulated. Reference design with higher values. Just to make sure that we understand the LCOE value for example, the black, which is the case scenario where the wind regime is A and we are using reference design. It's the upper part of the bar. And now we could say that the third task is accomplished. And finally, if for the energy yield per total cost of the system comparison, we also see that we obtain a higher energy yield per total cost of the system under an average wind regime. So we could say that we have accomplished all the tasks that we had to do for this quarter. Finally, we will make an economic assessment of a wind farm without an offshore substation in comparison with a wind farm with an offshore substation. And basically the only things that happen from one type of wind farm to the other is that here the array for the wind farm without offshore substation, the array cable system and the sport cable system will have the same voltage. And for the wind farm with offshore substation, the voltage of the array cables will be 66 kilovolts and the voltage of the export cables will be 20 kilovolts. And of course, we have an offshore substation. Here we have the assumptions that we were basically making the study for a case scenario where we are using a proposed design. And here we have the assumptions that we have taken. And also here, the assumptions in terms of the factors for the wind farm incorporated in the proposed design. What we obtain is that the wind farm without offshore substation obtains always lower fixed costs in dollars per kilowatt for a different number of 10 megawatt wind turbines in the wind farm. And here we see the largest decrease that we obtain, 4.31%, and the smallest decrease, 1.02%. And in terms of the LCOE values, we observe the same. The wind farm without offshore substation obtain lower LCOE values. And here we have the largest decrease and the smallest decrease. And I think that these last two slides of the economic comparison of both case scenarios are really valuable data because we get to observe that a wind farm without offshore substation can make a considerable impact in the economics of a project. And that's it. If you have any questions, please let me know.
So do we have any questions for either of the participants? Well, you guys did a terrific job. Nobody's asking any questions. I think that's very, very good. I want to thank you. And without any questions, I guess I'll do early dismissal. So are there any announcements we have to make? If not, okay. Thanks very much.